Good morning. Today we're going to be doing 8.4 normal distributions. The empirical rule. This is a property of normal distribution. Now, it's called the 68, 95, 99.7 rule. So what does this represent? The 68, that means that 68% of the data falls within one standard deviation. Of the mean. Now, the mean's going to be right here in the middle. This is going to be the mean. That represents the mean. Now, 68% lands within one standard deviation. Well, this is going to be the mean plus one standard deviation. And this is going to be the mean minus one standard deviation. So technically, within this region lands 68% of the data. The 95 represents 95% of the data falls within two standard deviations of the mean. So if this is the mean, one standard deviation, two standard deviations. So this is going to be the mean plus two standard deviations. And this one is the mean minus two standard deviations. So from here to here lands 95% of the data. And then the 99.7 represents the data falls within three standard deviations of the mean. So this would be the mean plus three standard deviations, the mean minus three standard deviations. So this represents the 99.7%. Now, anything outside anything more than three standard deviations away is called an outlier. Now, sometimes it's going to be asking like, how much is going from here to here? Well, if you think about it, if this is 68%, if I were to actually block this off, 68 divided by 2 is 34. So 34% of the data lands in this little region, 34% lands in this little region. If I take the 95 and I subtract the 68, and then now I have these two regions and I divide that by 2, that means that 13.5% lands in this right here, and 13.5 lands right here. Now, if I take the 99.7 and I subtract the 95, so I take all this out and then I divide it by 2, in this small section, 2.35% is, and here 2.35% is. So that's only if you break it all apart. Okay, let's get to some examples. All right. The population of NBA players is normally distributed with a mean of 6'7". So right here, this is going to be the mean. That is going to be 6'7". So I'm going to put 6'7". And the standard deviation is 4 inches. So if I add 4, 7 plus 4 is 11. So that'll be 6'11". And if I add another 4, you don't want to write 15 because remember, every 12 inches is a foot. So if I add 4, I'm only going to really add 1, and then it's going to bring my foot up to 7 feet. And then I'm going to have 3 inches. Add another 4, that's going to be 7'7". If I subtract a standard deviation, I'm going to subtract 4, so that's 6'3". Now, if you subtract 4 again, keep in mind, you're not going to write a -1. You're going to go down to 5 feet, 11 inches, and then subtract another standard deviation, so subtract another 4, so that's 5'7". Now it says Greg is considered usually tall for his school at 6'3". Draw the curve. Okay, so here's the curve. What percentage? Now let's see where Greg is. Greg is 6'3". So this is where Greg is at. Greg is right here. Now it says what percentage of NBA players is shorter than Greg? So right here, shorter than Greg. Now keep in mind that right here, when we did this curve, half of it's on this side, half of it's on that side. So Greg is just 1 standard deviation away, isn't he? Well, this small section right here was 34%. So if half is down here, I'm going to take 50% and I'm going to subtract 34%. So then that's 16%. So what percentage of NBA players are shorter than Greg? Well, 16% is. What percent are taller? Well, look, we have all this, the 50% plus this 34%, because this is where Greg's height is. So this is going to be a 34% plus a 50%, which is an 84%. Or you could have just taken 100 and took the 16% away. And then it says, how tall would a person be in order to be in the top 2.5% of the player's height right here? Because remember that this little section right here is 34%. This section right here is 13.5%. And then technically right here, all of this is the 2.5 right here, because that's what's left over out of the 50% here. So then the answer would be 7'3". 7'3" or taller. All right, let's get to another example. Scottish men chest circumference is approximately normal with a mean of 40. So here's my mean. That's going to be 40 inches. And a standard deviation of 2. So here I'm going to add 2, so that's 42, 44, 46. I'm going to subtract 2, so that's 38, 36, and 34. What would you expect to be the smallest and the largest chest measurements of the middle 95%? So from here to here, this was 68%. From here to here is the 95%. So the 95 would be the 36 to the 44. So here the smallest would be 36 inches, and don't forget our units. And then the largest would be the 44 inches. What would you expect to be the measurement of 16% of the men with the largest chest in the population? So remember at the very beginning when we separated this right here? So this little piece right here was 34%. And then this section right here was 13.5%. This section right here is 2.35%. And this section right here is actually 0.15%. So since it's looking at the largest, the 16 largest, it's right here. So it's going to be 42 inches and above. All right. Go ahead and try example C. I'll give you like a minute. Try example C. All right, if you're still working on it, go ahead and press pause. I'm going to go ahead and start going over this. It says math SAT scores are normally distributed with a mean of 508. So here's our mean. This is going to be 508. And a standard deviation of 121. So if I add 121, this is going to be 629, 750, and 871. If I subtract 121, this is going to be 387, 266, and 145. Find the population of students who earn SAT math scores in the following ranges. So it's looking from 266 to 750. So right there, that's 2 standard deviations to the left and 2 standard deviations to the right. That one is the 95% rule. On the next one, it says from 266, which is 2 standard deviations to the left, and 629, which is 1 standard deviation to the right. If we went ahead and we separated this, and this would be a 34% right here. This one would be the 13.5%, and this one would be a 34%. Now you're looking from 266 to 629. So you're going to add the 13.5% plus the 34% plus the 34%, which gives us 81.5%. Example D, a set of data is normally distributed with a mean of 80. So I'm going to go and draw this out. My mean is 80 and a standard deviation of 10. So this would be a 90, a 100, a 110, a 70, a 60, and a 50. And then it says, how do you use the symmetry of the distribution to find the percentage of values that lie between 80 and 90? So we want to know what this is. So remember that 1 standard deviation is 68%. So 68% of the data falls between 70% and 90%. Because remember, 1 standard deviation away is the 68% rule. And I only want half of that. Half of that is 34%. All right, I'm going to go ahead and flip it. All right, to compare different sets of data, we must standardize our normal distribution. Now, right here for standard normal distribution, it has a mean of 0 and a standard deviation of 1. Now, these are going to be used when you're comparing like two things that are on different scales, like the SAT score and the ACT score. The Z-score is known as the number of standard deviations a data value is above or below the mean. And it's going to be the data value minus the mean divided by the standard deviation. We will be using our calculator and Desmos on this. Okay. It says a set of data with a mean of 13. So here's our mean. Our mean is 13. The mean is equal to 13. And a standard deviation of 3. A standard deviation of 3. So this would be plus 3, plus 3, plus 3. Minus 3, minus 3, minus 3. Now keep in mind, they said the mean was going to be a 0 and a standard deviation of 1. So it's going to be, this is going to be 1 standard deviation, 2 standard deviations, 3, -1, -2, -3. Now it says find the Z-score for 4.3 hours. That is going to be your data value. So that's going to be X. So your Z-score is going to be the data value, which is 4.3. Subtract the mean. The mean was 13. Divided by the standard deviation. The standard deviation is a 3. So when I type this in my calculator, I have a 4.3 minus 13. That's left with negative 8.7. Divide that by 3, and I get a negative 2.9. On this next one, it says, how many hours is a Z-score? So now I'm looking for the X value of 1.33333. So this is going to be the Z now. So I'm going to set 1.3333 equal to, now I don't know what the X is. I'm trying to figure that out. Minus the mean, which is 13, divided by the standard deviation of a 3. I'm going to multiply both sides by a 3. So now I get 3.9999 equals X minus 13. This is technically going to be a 4. And when I add 13 to both sides, 17 equals X. So this answer is going to be 17 hours. Now we want to find out what percent of all the data will have a Z-score of less than 0.75. I'm going to show you how to use this on the graphing calculator, and then I will show you how to do it on Desmos. So on the graphing calculator, what we're going to do is I'm going to write the steps on the left side. We are going to hit, so this is on the TI-84 or the 83. You're going to hit second, and then you're going to hit vars. So you're going to hit the second button, and then you're going to hit vars. Now right here, you're going to go to option 2 where it says normal CDF. So hit option 2, normal CDF. So now here, when you're doing this, it's going to be normal CDF. You're going to go ahead and leave it as -1 e to the 99 power. That's basically going to be a 0 because you want all the numbers from 0 to 0.75. So -1 e 99. Now the upper is going to be the 0.75 because you're looking at all the numbers from 0 to 0.75. And then this is always going to be a 0 and a 1. And there's my answer. The answer comes out to be 0.7734, which is 77.34%. 77.34%. All right, now we're going to go to Desmos. So on Desmos, let me share my screen. On Desmos, and I will write this down. You're going to go to functions right here. Then you're going to go to distribution, DIST. You're going to click on normal distribution, which is right here. Now you need to click this CDF button. You have to click the CDF button. Now your minimum is going to be negative infinity, which is going to be 0. And we're going to go up to 0.75. And look, there's the answer, 0.7734, which is 77.34%. So for Desmos, you're going to hit the function key. You're going to go to the option that says DTST. Then you're going to hit on normal distribution. You have to click on the find CDF. And then for this one, your min would be, you'd leave it alone. And then the max, you would just leave it at 0.75. Okay, let's try the next one. On this one, where it says find the percent of all the values of Z greater than negative 1.4. So if you're actually looking at a number line, if we're looking at a number line, here's 0, negative 1.4 is over here. I want all the numbers greater than this. So just keep that in mind. So I'm going to go ahead and I'll use Desmos on this one. Now, when I'm doing my normal CDF, I'm going to still leave it as negative infinity. But what I want you to recognize is because I'm leaving it as negative infinity, it's going to be the left side. So whatever you get, you need to take that away from 100 because you want the one that is greater than the negative 1.4. And then I'm going to calculate it at the negative 1.4. So remember, whatever answer it's giving me this side of it. So let's share my screen. So I'm going to hit functions, normal distribution. I want to find the CDF, the cumulative probability. And now the maximum I'm going to put as a negative 1.4. So that answer right there, I'm going to write it down, is a 0.0808 because the 5 is going to make that round up. Now, that is technically 8.08%. But remember, this is this part right here. I need the Z-score to be greater than the negative 1.4. So what I'm going to do now is I'm going to take the 100% and I'm going to take away the 8.08%. So the final answer here is 91.92%. Because I'm looking for what is greater than the negative 1.4. All right, this is a great example of using the Z-score because we're comparing two different data sets. SATs on a different scale as the ACT on scoring wise. So right here for SATs, it says the mean is 1,000 and the standard deviation is 200. Now, an ACT, the mean is 21 and the standard deviation is 5. Do you see how the scales are completely different? These are in the thousands and these are not even more than 100. How does the SAT score of 1,120. So that's going to be your x. So right here, the x is going to be 1,120. And then right here, it says the ACT is going to be 23. So I'm going to find my z-score. It's going to be x minus the mean value divided by the standard deviation. So here my z-score comes out to be 0.6. On here, I'm going to do 23 minus my mean, which is 21, divided by the standard deviation. So this z-score is going to be 0.4. This one is a higher z-score. So the SAT score is better. Like if you were to actually draw this out right here, the mean would be 1,000 and the standard deviation is going to be 1,200. I mean, it'll be 200. And you're looking at an X score of 1,120, which is right here. If I were to draw this one out, my mean is 21 and my standard deviation is 5. So this would be a 26, but I'm looking at a 23. Do you see how it's hard to compare them just by the graph? Find the percentage of all values in a normal distribution where the z is less than 1.85. So I'm going to do the normal CDF. Now I do want the ones less than negative 1.85. So if I looked at my number line, here's 0, here's 1.85. I want everything to the left. So when I don't have to worry about subtracting it from 100 because I am looking at the left side of it. So I'm going to still do the negative 1e to the 99. Now I'm going to type in 1.85 and it's going to go from 0 to 1. So let me pull up Desmos. Function, normal distribution, click on the find. And right here for the maximum, I'm going to hit 1.85. And that answer comes out to be 0.9678, which is 96.78%. Now right here it says, what percent of the data is between negative 0.8 and 1.3? So I'm actually going to have to find out both of these here. So normal CDF. First, I'm going to do the 1.3 because that's the largest. Now think about it. So if I do the 1.3, 1.3 is right here. I'm going to get all of this. And then whatever answer I get, because I only want to go from negative 0.8, I'm going to subtract this piece of it. Because if I subtract that piece of it, then I'm only looking at the middle piece right here. And that's eventually what I want to get. Sorry, the lights just turned off. So then I'm going to have to find out what this one is. So whatever answer here, that's going to be all of it. I'm going to subtract this one right here so I can only get the middle section that I want. So let's go to our Desmos. I'm going to type in a 1.3. and that answer comes out to be a 0.9032. Then I'm going to type in the negative 0.8, and that answer is 0.2119. This one as a percentage is 90.32. This one as a percentage is 21.19. So my answer is going to be 90.32% minus 21.19%. So my final answer here is 69.13%. Now, why is a z-score a good measure to use to compare data from two different normally distributed data sets? It normalizes the data. That's why. And that concludes our notes for today.